My name is Corey Conrad, and I work with Google.org's Predict and Prevent initiative. We're predicting and preventing emerging threats, and our initial focus is on emerging infectious diseases. And in that light, I am thrilled to introduce you today to Healthmap. Healthmap is one of our early grant recipients and initial partners in earlier disease detection. And they're a really cool organization focused on detecting diseases as early as possible through a multi-stream, real-time surveillance platform that continually aggregates reports on new and ongoing infectious disease outbreaks. Healthmap launched in September of 2006 and has since been featured in a number of mainstream media and scientific publications. These include Wired News, The Lancet, Nature, and Science. They've also published peer-reviewed articles in a variety of journals, with a recent publication in PLOS Medicine, which is definitely worth checking out if you haven't read it already. Today we're joined by co-founders Dr. John Brownstein and Clark Freifeld and their colleague Dr. Mikaela Keller. John was trained as an epidemiologist at Yale University and is assistant professor of pediatrics at Harvard Medical School, where he has joint appointments in the Children's Hospital Informatics Program and the Division of Emergency Medicine. Clark is a research software developer at the Children's Hospital Informatics Program. He studied computer science and mathematics at Yale, and his main interests include web-based UI design, data visualization, text mining, and technologies for developing countries. And Mika is a computer scientist specialized in statistical machine learning. She's focused on developing approaches to enrich text representations by incorporating knowledge gained across large, unlabeled data sets. Before joining CHIP, the Children's Hospital Informatics Program, where Healthmap resides, as a research fellow, she was a PhD candidate at École Polytechnique Fédérale de Lausanne in Switzerland. So please join me in welcoming Healthmap as they give a tech talk today.
Great. Well, thank you so much for having us today. We're really delighted to talk to you about our project, healthmap.org, which is a global disease alert map designed to scan the web for reports, early reports on disease outbreaks. So I'm just going to start by giving you an example. This is a recent Salmonella outbreak that we experienced in the U.S. over the past summer. We all know the Serrano pepper was implicated. And we can see the spread of this outbreak emerge through the U.S., starting in New Mexico, but eventually making its way to over 40 states. Now, you would think that this data was actually coming out of an organization like the CDC or a public health department. In reality, this data came to us through Google News. And in fact, the first report that was identified that we could find across the web was not a CDC report, but was in fact out of Las Cruces News, Sun News. And it really indicates to us the potential value of mining the informal news media and other resources for the purpose of public health. And in fact, if we look at Google News versus the CDC reporting, the eventual CDC reporting, they actually line up quite nicely. There are some places where the outbreak is actually reported first in certain states in the news compared to the CDC. And in fact, if we look at the epidemic curve, the first reports that we can identify across the web really came out of the informal reporting. And well before New Mexico reported on the outbreak, and even further before the CDC report came out. But this example is not necessarily a link to a US specific. If we think about the reporting of SARS and what happened over the time period in which SARS developed in China, in fact, the first reports here, once again, were not actually out of public health agencies, but in fact, out of the news media. One example is very early on, a pharmaceutical company released a financial report discussing cases of atypical pneumonia, followed by Chinese language media reports coming out about a cluster of cases happening in Guangdong province, as well as an astute physician on a mailing list called ProMed that was discussing problems emerging in school children. And this was well before the WHO was actually reporting on this information globally. And in fact, really, their official report came well after the Chinese report came. I mean, the report of the outbreak in the Hong Kong hotel that eventually led to the spread worldwide. So in fact, the sources of outbreak news that are in fact go on to be verified by the WHO really come out of these types of news sources, these wide informal data sources that really are of much greater value than some of the other more traditional data streams that one might think of when you think about verifying a disease outbreak around the world. And so when we think about the types of data, the traditional surveillance sources, there are some really important limitations, especially when you think about global surveillance, the issues of lack of infrastructure and training and gaps in coverage, and especially when we think about information flow as what happened in the SARS outbreak. Then when we think about informal surveillance, so the surveillance of rumors and news media and other data streams that we can find and mine on the web, we really see that this is an abundant and cheap resource that provides detailed and near real-time reporting and is really less susceptible to political pressure. So we've really focused our attention on thinking about these types of data streams and how we can really harness the power of what's out there to better understand the global burden of infectious disease. But this concept of internet-based searching is not a new one. Other organizations have looked into this concept, but what we saw as we developed Healthmap was that there was a tremendous amount of data out there and really no comprehensive system. So, and one other issue is that this information is often unstructured and free text, and it's not categorized in any useful way, and it's not brought together. And each data source has its important gaps in geography and expertise and population. And so really what we are trying to do is think about how to integrate all this information into one common platform to create that sort of synthesized view of global health. So this is why we created Healthmap. It's at healthmap.org, and it's essentially a system designed to query and mine and scrape the web for reports and bring this all into one common interface so that anyone can get to this site and look at ongoing emerging diseases. So today I'm going to be talking to you a bit about the system overview, and then followed by that, Clark will actually give a technical description of really how the system works. Mika is actually going to go on to talk about ongoing research objectives, and then I'm just going to end off briefly with some research directions, future directions for the system. So what are really our objectives? I think I already outlined that, but essentially the idea is that we want to enhance surveillance through integration. So data fusion is the big term right now. So the idea of bringing in news wires, RSS feeds, mailing lists, anything that we can get our hands on that we can then automatically scrape and categorize and filter and provide into a common interface. And the idea is that we integrate all information about a given situation to produce a meta signal or a combination of all the information about a given outbreak. And so the idea is that we can achieve this unified and comprehensive view of health in both space and time mapping. And really, one of the major objectives of the system is that we limit information overload. So we all know that when one outbreak gets reported, there's an AP story. This gets flooded in the media. And really, the idea is to limit the duplications, filter out the data, and really just make the most important information available to the user. And really at the heart of Healthmap is a free and open system. So we really rely on open source technologies and open APIs like the Google Maps API. And so really the idea is that the system remain free and available to anyone who wants to use it. So when we think about who wants to use it, well, there's the public health. So public health agencies we know that use a system like the UN and WHO for keeping abreast of what's happening in the population. But on the other hand, we also have a real interest in developing a resource that's of use to the general population. So we want it to be available to someone who's thinking about traveling abroad and thinking about how to prepare, what to do in terms of vaccinations, thinking about individuals who just want to know what's happening around them. So it really has a purpose for anyone really who's interested in public health. So in terms of our usage, we have tremendous variability, but essentially about 1,000 to 10,000 unique visitors every day. About over 500,000 since its launch, and really the top visitors are in fact right now from government agencies like the CDC, WHO, Homeland Security. These are some screenshots actually of current implementations of Healthmap in command centers like in HHS and the European Union. And in fact, right now we're doing surveillance for the upcoming national conventions in Minneapolis and Denver, and so we're providing feeds of our data to those ongoing surveillance activities. So how does the system work? Clark's going to get into really the nuts and bolts of the system, but the idea is that we come up with a report. This is a news report of bird flu in China. Our system is able to detect and scrape specific keywords, whether it's China, bird flu, and then specific language around the type of disease and specific localization of that particular outbreak. As soon as that article gets posted, within the hour, it would end up on Healthmap. So if someone was interested in avian influenza, they would filter by avian flu and then be able to then look at all current avian influenza reports. If they're specifically interested in China, they zoom in there and then get access not only just to that report I showed you, but all other ongoing reports that are happening about avian influenza in China. And so someone can get a very broad view of all ongoing alerts and articles about a given situation. In fact, actually just 5 minutes ago, we just implemented a new view of Healthmap, which is using the Google Earth plugins, and now we have an even better visualization tool to actually start really focusing in on specific areas and getting additional data layers. And another view of the system is actually a situational awareness tool. So we don't only provide the map interface, but the idea is that we can put all the articles together about a given situation, whether it's avian influenza articles happening in China or just other outbreaks happening in a given location. We can put all this information together into one common framework so someone could get all access to that information right away. So in terms of the amount of data that we're collecting, right now it's at about over 200 outbreak alerts per day, with over 100,000 collected so far. So we're talking about a fairly large amount of data. And compared to the fact that, for instance, the WHO only reports maybe one outbreak per day over a given year, you can see how in one particular day we're already collecting more than what the WHO might do in a full year. And our alerts are global, so we're getting, right now we've covered about 201 countries, over 175 diseases, and right now we're searching in five languages. So in terms of the geographic representation, as I mentioned, we have fairly good coverage across the globe. Obviously, there's a bias in the news media towards places with more technological development, so we'll have a bias towards, for instance, outbreaks in the US and the UK and other places. Important to note is that we do have a gap in parts of Africa, and that's really important to us to figure out how to start to fill in those holes, whether it's through languages or through other types of data that obviously is not available electronically. We're thinking about ideas like SMS messaging, and so other ways to fill in those holes. So we recognize that there are other types of data that we need to be pulling. In terms of the diseases we're collecting, we have a broad variety of infectious diseases. And once again, we have a bias towards avian influenza, things that are right now in the media spotlight. And so those are the types of things that we need to account for when we think about how to properly treat our data. So there is a focus, but we do have a fairly broad range of infectious diseases that we're reporting on. One thing that we're also interested in is the types of sources that we're reporting on this data. So we are hoping to potentially find certain sources that are the early reporters, the great news sources that provide us the key data. But in fact, what we find is that there is no one source, that there's many, many sources that are the first to report on a given outbreak. We do have particular resources like allafrica.com or Xinhua that are regionally specific, so we get very good regional coverage. But what it really comes down to is that we really need to be monitoring all these sources of information. What we're also interested in is reliability of news sources. And this is a very difficult question and fairly difficult to answer. One way we've tried to look at this is how does a news story begin to get replicated in the media? And if a news story is taken from one source to another, is that maybe an indication that a potential source is more reliable? And so we're building in reliability scores for the data to really assess how much confidence we have that an outbreak is happening. And this is important from the perspective of the issue of, for instance, inserting a false report into, say, Google News somehow that would then get fed back onto the map. So we're very concerned with how to properly validate the system, and I don't have time to go into too many of the details around many of the different studies we're involved in, but one of the areas is around thinking about how to think about the timeliness of our reporting. And it's very difficult to actually get a good gold standard of all ongoing outbreaks that are happening around the world at any given moment. In fact, though, the WHO does do a very good job of reporting on avian influenza cases. So for us, what we can do is begin to think about when a particular case began and think about the time at which then it was reported in the news and then followed by that reported by the WHO. So one thing we're doing is, for instance, this is a cumulative case count of avian influenza over 2007. And the light blue area represents the time in which the case was started, the date in which the case was started. The dark blue represents the time lag to the actual report in the news media. And we see it still takes a bit of time before that case reaches the media, about 9 days. But what we've seen is, in fact, that lag is still smaller than what we get reporting in, for instance, from the WHO, where the lag is still a few days after that point in time. And I think a lot of our work is going to be directed at thinking about, okay, what is the baseline reporting, and how do we keep trying to improve our mechanism? How do we keep shifting that timeliness and make that smaller? One other way that we're trying to evaluate the data is, since we've only been in existence for 2 years, is to think really historically. And one way we've been doing that is looking back in time. This is an historical time series of influenza over the last 70 years, and to think about how to match that with data that we can still mine from Google News archives. And so if we in fact look at the time series that corresponds to that, this is in Google News archives, that these time series are actually incredibly well matched, both in terms of their cyclic behavior as well as in terms of their magnitude. And so it's giving us some perspective into how the news media reports, and in fact the quantitative aspects of the news media volume track very, very incredibly with the actual population level burden. So we can do things like track the news media in terms of, this is the 1918 pandemic, thinking about the news media is actually analogous to public health data. And in fact, we're doing a variety of investigations to think about how the data, this informal data, really is a great adjunct to traditional public health surveillance. This is just an example of specific city-level burden and news reporting out of a Google News archive, and how this particular data does match up very well with the actual burden that was experienced in those particular cities. So I know that it was a sort of quick overview. I'm going to stop here and then turn it over to Clark, who's actually going to talk really about the system and how it works and really get under the hood of it. So I'll turn it over to Clark.
My name is Clark Freifeld. I'm a software engineer at Healthmap, and I'm going to sort of pull back the curtain a little bit and run through some of the technical details behind the system. I'm going to present a lot of details and numbers and things, so I apologize for sort of moving quickly through, but obviously if you have questions, you can certainly ask. Just to give you an overview of what we're trying to accomplish with the system, you can consider the sort of the whole universe of available data, basically the entire internet, and then consider the small subset of that, which is health-related reports of any kind, and then another subset of that, which is the data, the reports that the Healthmap system is potentially capable of collecting, and then again a subset of that, which is the reports that are actually that we want to display that are actually relevant to our mission of tracking disease outbreaks, and then finally within that, the very small circle is the subset of reports that you as the user might be particularly interested in. So maybe you're interested only in reports that have international significance, or only reports for a particular location or a particular disease. So that's the idea. So the first step of the process is the acquisition of the reports. Through news aggregators such as Google News, we hit roughly 20,000 sites every hour on the hour. The next step is extracting the primary location and primary diseases for the report. The next step is categorizing the reports into these 5 different categories. Really what we're primarily interested in is that first category, breaking news. So that's any report that refers to an actual currently ongoing outbreak. What we call a warning is generally like a disaster situation where no actual cases have yet been identified, but disease outbreak is considered to be imminent. Old news is like a follow-up report about a previous outbreak, like a lawsuit or a Senate hearing, etc. Context is kind of a catch-all for things that may be health-related, but are like outcomes of scientific studies, pandemic planning, vaccination campaigns, other types of news. And then not disease-related, I think, is self-explanatory. The last step is aggregation. So as John mentioned, when a big story hits the news, many different sources will report on basically the same event. So what we have is some algorithms for collecting those reports together, so that on the map you see basically that first report only, rather than being flooded with all the repeats. So the reports are collected. They go through that process of automated algorithms, and they get posted directly to the map. At the same time, we have this administrator interface which allows us to review the reports as they're coming in and make corrections to the potential misclassifications of the algorithm. It also so it improves the output of the system, obviously, but it also allows us to track the performance of the algorithms and improve them as we go. Another sort of prototype feature that we're working on is email alerts. So you can get a customized subset of reports delivered to your inbox, and then there are also links embedded in that email which allow you to click directly through to the administrator interface and correct misclassifications as they occur. So getting more in depth on the acquisition phase, we collect reports from various sources, mainly news aggregators, also mailing lists of infectious disease specialists. So one key area of our research is looking at which are the best keywords to use. We want to do searches that will give us a high yield in terms of the maximum number of articles that refer to actual ongoing outbreaks, while also minimizing the number of reports that are kind of not what we're interested in. So, those pandemic planning, et cetera, et cetera. So, and then another challenge we have with that is as we expand into other languages other than English, we're currently operating in 5 languages. How do we, again, find those words in different languages? Because, for example, we use the word outbreak in English. It works pretty well in terms of pulling out those relevant reports. Well, other languages don't necessarily have a really close synonym for outbreak as we use it in English. So that's an ongoing process in each language. So we extract various data from the reports as they come in, and we also pull out the actual textual content of the article using a neural network system that Mika developed, actually. Again, as I mentioned, we're collecting reports in 5 different languages. We're sort of just getting started with some of the non-English languages, but that gives you a basic breakdown of what we're doing. With that, moving on to the extraction step, this is where we pull out the disease and location for the report. So it's what we call a dictionary-based approach, or gazetteer. So what you see in the upper left there is an extract from the dictionary file. It consists of a list of text patterns matched with a list of IDs for the particular item. We have about 600 different locations worldwide, so that's all the countries, and then states and provinces for several different countries, and then 200 different disease categories. And then the dictionaries consist of about 7,000 different text patterns which map to these 600 locations and 200 diseases. So for those technical people in the audience, basically we load this dictionary into memory, into a tree like that, and then process the text word by word, matching it to the elements of the tree. And if we get to a leaf, which is an ID, then that means we have a match. So there's certain advantages to this approach. One is that we can get started right away without having to build up a training set of human curated reports, because we can basically just take a list of countries, generate a dictionary from it, and get started. The performance is pretty good because it's linear on the amount of text that you're processing. The articles are pretty short, so. And this is it's particularly important because we're expanding to different languages, so we need to be able to generate that dictionary rapidly as we start with new languages. There's obviously some problems with this approach. It's fairly rigid because it's rule-based. We don't really have a good way of disambiguating place names. So like most of the time, London refers to London, England, but there's also London, Ontario, and London, Georgia. And so the system doesn't really have a good way of distinguishing those different types of situations. Mika is actually working on a more flexible machine learning-based approach to addressing some of these issues, and she's going to tell you about that shortly. So in spite of those drawbacks, the performance is reasonably good. Basically, won't get into too much detail, but basically we can look at, well, out of the alerts that we collect, how many of them required some sort of correction to the classification that the system did. And from that, we can compute what the accuracy of the system is. Another area that we're exploring is not only improving the accuracy of the location extraction, but also getting beyond that list of 600 locations. Obviously, there are many millions of places that are named around the world. And this is a tool that we've developed for building a training set, getting into more richer location databases. Third stage is the categorization to the categories as I described. This gives you a picture of what the distribution of them, and it's basically 50-50 between breaking and context. So that's really kind of the key distinction that we look at analyzing the system. So if we consider a breaking news alert as a positive and a non-breaking news alert, so essentially context as a negative, then we can compute sensitivity and specificity statistics for the performance of the system. So basically, just to review, maybe if you're not familiar with the term, so sensitivity basically gives you a measure of how well you're getting the true positives, and then specificity says how well you're identifying the true negatives. That's the rundown of that. Final step is the aggregation, collecting duplicates together. Again, I won't get into the details of exactly how it works, but basically we do a textual comparison of the different elements of the report. One key component of it is that we actually consider the frequency of words. So if two different reports have a very rare word in common, then it's very likely that they're referring to the same event. Whereas if they have a very common word in common, then it could be that they're completely different reports, just happen to have this same word in common. And then the nice thing about this system as it's set up now is that it pretty much works out of the box for new languages, so we don't really have to do a lot of build-up work to make that work. So again, you can do some analysis of this by assigning a positive and a negative. So basically, a positive is when one alert is truly similar to another alert. A negative is when an alert is unique. So again, those are the numbers for that. And then we can also kind of step back and look at the overall performance of the system. So we basically consider what we call visible alerts versus invisible alerts. So what's visible is something that is breaking and a primary, so not a duplicate of another alert. And then we look at, well, how many changes do we have to make to the system that would be actually visible to the user, as opposed to kind of updating metadata behind the scenes. And that sort of gives you a rough breakdown of what the system is doing. So the green circle is the set of alerts that are visible, and it ends up being about 20% or so of the total reports that we collect. And then, again, if we take visible as a positive and invisible as a negative, we can compute the sensitivity and specificity statistics. So looking at this, you might say, well, the specificity is obviously pretty high. The sensitivity is not so high. Why would that be when this is a disease outbreak tracking system? You'd think, well, it's okay to have a few junk reports come into the system because it's really important to be able to detect the next outbreak of SARS. So why not sacrifice some specificity in order to gain sensitivity? So the answer to that is basically because there's so many reports that we collect, you can see the raw numbers there, that are actually junk reports. If we sacrifice the specificity, then the volume of junk alerts that's going to flood into the system is actually quite high. Okay, so that's the basic rundown of what we're working on, what we have running currently. There are obviously a lot of different areas where we're looking to improve all these algorithms. In terms of acquisition, we're expanding to different sources, trying to fill in the gaps where, as John mentioned, we have a heavy focus on the U.S. and other industrialized countries because those are the ones that have the most active electronic media. So we're working to fill those gaps. We're adding in clinical sources like the GeoSentinel network, which is a network of travel clinics, adding more languages, and then improving the algorithms that we apply to the incoming alerts. As I mentioned, getting beyond the 600 locations that we use. Also extracting other aspects from the report, like the number of cases, the number of deaths, et cetera. And then we're also bringing in people from the outside to make use of that administrator tool to sort of build a community around this and kind of spread the work out of building training sets and correcting the algorithms. And then finally, we're working on improving the front end, so creating richer visualization, better customization, and linking up with other systems like ProMed, and John will speak about that more. So with that, I'll turn things over to Mika. Thank you.
Hello, everyone. My name is Mikaela Keller. I'm doing a postdoc in the Healthmap team, and I'm going to talk about some ongoing research. Sorry. So we've been interested in looking back at the data we've collected for 1 year, for obvious reasons. For example, for use it as a training set to be used to improve the outbreak detection and characterization, but also because we want to be able to compare the data we obtain with the data that WHO that was verified as being true outbreaks, and also because we want to make analysis of epidemiological. We want to discover if there is epidemiological patterns ongoing each year. And so, for example, in the case of the timeliness verification, you kind of need to single out each outbreak to be able to compare it with the verified outbreak. And this is not so trivial to do because the outbreak we detected, or the outbreak, to do it automatically, because all this information is extracted from free text, which it's always a little bit ambiguous. However, how is an outbreak characterized? An outbreak is characterized by the ongoing disease, the location where the outbreak is taking place, when is it taking place, and who is involved in this disease, the patient, for example, the number of cases or the sex or the age of the patient. And so traditionally in natural language processing, this is described as the task of information extraction, automatic information extraction. And so Healthmap already does information extraction, as Clark explained. For example, the disease, the location, and the time windows are taken into account by Healthmap. But we would like to have a more precise. We would like to assess the force point and also have a more precise geographic location. And so what I'm going to present is a subtask that can be probably generalized to these other information extraction problems, but I'm going to apply it particularly to the geographic location extraction. So I'll first will present this subtask, which is the geo-parsing, then explain the method I have developed, and then some experiments. So the end task is called geo-indexing, which is in fact associating to a document a geographic index. This usually involves somewhere or other a gazetteer, which is a list of geographic keywords with their associated index, which could be, for example, latitude, longitude index, or in the case of Healthmap, it's a country code. And somewhere else in the process, there's also what I call Geo-parsing, which is called Geo-parsing, which is the extraction from the text of the geographically relevant keywords and phrases. So finding into the sequence of the sentences, where are the location phrases. Okay, and so that's what my system is going to be about. Okay, so how do humans do geoparsing? When you see this sentence, investigation into measles outbreak in Lung in Belaga district revealed the cases originated from penants living in rapid and unsanitary conditions. I don't know any geography about Malaysia, so then I look it up. But before, when I look this sentence, I'm still able to find out that Longurun and Belaga are places, but that Penang is not a place. And that's because we rely mostly on the context, not only on the words. We don't rely on the keywords, but in fact in the context, and the context in terms of syntax, term of capitalization, maybe also vowel distribution, since often the location are foreign words, so they don't have the same vowel distribution as the surrounding words. Okay, so that's something that we want to exploit, in fact. So automatic geoparsing, it's, as I say, an information retrieval problem. And recent approaches to information extraction problem. And recent approaches to information extraction problems, such as name entity recognition, semantic role labeling, have been to have, so the statistical approaches have been to rely on heavily annotated data sets to learn where to extract the information. And so these data sets are expensive to obtain and take a long time, and you probably Google doesn't have this kind of problems, but when you're a group of 3 people, you want to think of something else before going into labeling data sets. And so what we have is that Healthmap is already working, and that we have a purposely crafted gazetteer, which is, I'm going to show you a little bit an example in a moment. It's really designed for the kind of task we're trying to solve. And also, as Clark said, we're mapping to 600 places, but in fact, in the list, we have access to 7,000 location name. In fact, the gazetteer is much bigger. Okay, so an example of the Healthmap gazetteer. You can see here there are country places, country words, country references, city references, but also colloquialisms such as Aussie announce, that's Australia. Also some really medical related terms of Japan, Bangladesh. Hospital is somewhere in Bangladesh and not in Japan. And CDC, when we see CDC by itself on an alert, so there's a big chance that that's American-related disease, or INSERM is a French-related disease. And in the same time, we also have negation, like Brazil is not a place. It's Canada Goose is not in Canada. Okay, so that's what the gazetteer looked like. And so the idea we'd like that we develop is that we will use the gazetteer to label data set, then augment the information by adding linguistic information, such as the part of speech. Is this word a verb? Is this word a subject? Is this word things like that? Also highlight the capitalization status. Is this word in capitalization or not? And if we stop there and just use this data set to do training, we will just learn by heart the gazetteer, which is not what we want. We want to be able to generalize to words that are outside of the gazetteer. And so for that, we played like hiding the information. Like you see in this example, I'm hiding New Caledonia, but if you read only the second sentence, you still know that in this place there must be a location. So that's what we also give to our learning algorithm. Okay, so now I'm going more into the detail on how this was implemented. I hope I won't bore you. First, how we integrate all the different information that we add to our words. So we represent words as a big sparse vector in which the first components are for the lexical information, which we call dictionary index. The second part is reserved for the part of speech index, and the last part for the capitalization status. Now, how do we implement the hiding the words? For that, we in fact take advantage of the natural distribution of location words into the more general words. And so what you see in the graph is that if I hide the words that appear less than 5 times, for example, the first point in the graph, that concerns 5% of the words, but 20% of the location references. So if I cut my dictionary, removing all the words that appear less than 5 times in the data set, I'm hiding 20% of the location. So that's the way we manage to implement this hiding of the lexical part. And so we label our data set using these things I showed you before, and we use the data set to train a neural network which outputs the probability of being a location or not, given a word and a window surrounding this word, so a context of several words. And so this architecture was inspired by a language model presented by Benjel and all, and also more recent work by Colobert and Wesson on a semantic role labeling tagger. And so, yeah, I may not go too much into detail, but there's 2 phases. One which is only mapping the words into a more rich space, a more rich representation, and then using this new representation to actually answer the question of whether or not this is a location. Okay, so now I'll quickly go through the experiments. So we built a training set from the disease outbreak alerts that were retrieved by Healthmap in 2007. 2,500 alerts, which in fact it's more than 1 million words to tag, so it's not that small. I trained several neural networks, fixing the size of the context and fixing the size of the representation layer. Tuned then a lot of hyperparameters, others, and tested several cutoff of the dictionary. So just to understand what's happening there, so in the validation, what the result you're going to see, it's on a separated validation set. So in a training set, you train the neural net with knowing the answer. In the validation, you don't know the answer. The answer is apart, and you look at what would be the answer of the neural net and match the true answer with the neural net answer. And so what you see here, the plain blue line is the performance of the neural net in terms of F1 score, which the only thing you need to know is that the higher, the better. So when I hide, and the x-axis is I'm hiding more and more location, so I'm making the problem more and more difficult. And so the F1 score decreases, which is normal. I'm making the problem more complicated. But if I then decompose this error on looking only at the words that were hidden, so the neural net didn't have the lexical information, Longuru was out of his dictionary, then that's the red line. And the more I train the neural net with hidden words, the better I am to discovering words that were out of my dictionary. That's the more I'm generalizing. while in the same time I'm not losing too much performances in the words I have access to, which is encouraging to see that I'm able to discover new words that were out of my dictionary, kind of given a hint that that's a good idea. And that's also to show that the context is worth something. Okay, so when I increase the size of the context, I increase the size of increase the performance. So that's it. So I've shown a method that transfers prior knowledge encoded in a rule-based approach into a statistical learning approach. This could be generalized to other information extraction problems, and have shown that this methodology helps discover geographic references based on the context only. And there's a bunch of other tests that must be done, but we're doing them. Now, John, give back to John.
Great. Okay, yeah, so we just going to quickly wrap up just telling you about what the future vision of Healthmap is, because Mika really outlined really impressive way that we're trying to advance the technology. What we're also trying to do is engage users and really think about the public health element as well. So in parallel as we're developing the technology, we want to think about how we engage users and really the human network. And that has proven value in other systems like the ProMed system. And really the combination, the adjunct of the automation plus the collaborative filtering approach really is sort of the ultimate goal for the system, because there's only so much that a technology can really do. And to have people in the field validating and reporting information is sort of the way we see the vision of this system going. And so right now, really, the reality of the system is that Healthmap is out there sucking as much data as it can and bringing it out there and exposing it. But we don't have the linkages back into the field. And that's why we're really trying to develop collaboration, especially with organizations like ProMed and others, like TefiNet and other organizations, to produce an automated feed and really help them in terms of their work and thinking about how they can improve their job, but also at the same time bringing data back into the system, whether it's through new posts or through filtering and editing of the information that we're already collecting in Healthmap. And this has added value for a number of reasons. One being that we can just bring in new content. Two, that we can improve timeliness of reporting, so by bringing in that information, but also helps us in our precise classification, annotation, verification. And finally, as Mika said, we really do need a training set to keep improving our automated technology. And so building a high-quality training set would also be the outcome of such an approach. So I'm going to wrap up here. I know that we want to have some time for questions. But really, I mean, I think we see some real value in bringing all this data together and really an approach to integrating and creating a real view of the world that complements traditional public health surveillance in a multilingual collaborative environment. And really, the idea behind Healthmap is to provide this customized, real-time intelligence view of ongoing outbreaks for the broad scope of all international public health efforts as well at the individual level. So I'll just thank the people from our group and a bunch of the volunteers that have actually helped us develop a lot of language-specific capabilities. Obviously, big thanks to our supporters at Google.org and Mark Smolinski, Corey Conrad, Larry Brilliant. Without that support, we really wouldn't be where we are right now. So thank you so much, and we're happy to take questions. Thanks.
Who are new to using Healthmap, the category of uncategorized disease, I think it was, or not yet categorized, seems very interesting. Is that something that you're planning to refine or use, for other organizations?
So, I mean, yeah, you want to go for it? Go for it. Yeah.
Yeah, that's a good question. So, basically, as I said, we have this dictionary. We have 200 or so disease categories, and then a dictionary of a few thousand text patterns that map into these disease categories. Basically, when we a lot of times we'll capture a report that refers to, let's say, a very rare disease, one that we don't have in our list of 200. It's not in the dictionary. We still want to be able to put that up on the map. So we just use this not yet classified sort of catch-all category. The other way we use it is we actually have a list of very rare diseases that we just they don't occur often enough really for it to be worth it for us to put those into our list of 200. But certainly as we develop the system, we're going to be adding more and more diseases and looking at the relationship between disease types and symptoms and definitely improving that. I mean, the goal is to have as little of the not yet classified as possible.
But what about things like SARS, which are, if I remember correctly, when it was discovered, it wasn't named.
Right, exactly. So we definitely want to be able to pick those up. So that's part of the motivation behind. Well, okay, the algorithm didn't pick anything up, but that doesn't mean that this alert is no good. As John points out, we do also have another disease category called undiagnosed. So a lot of times we get reports, saying mystery illness, in Vietnam. So that maps to undiagnosed. So that's another category that you look at.
We can also take questions from those who have VC'd in. So if anyone in San Francisco has questions, feel free to unmute your mic and ask.
I'm actually just kind of wondering what effect Healthmap has had, if any yet, on kind of the content producers, like the reporters that write the articles that you kind of scan. I mean, it seems like them knowing that you're kind of searching this might provide some sort of opportunity for collaboration where they could embed some sort of tag for you to analyze or something of that sort.
Yeah, that's a great point. I mean, we've actually been linking up with some disease-specific reporters around just giving them feeds of information. There's a reporter by the name of Helen Branswell in Canada who's following the avian influenza story, and so she's getting right now an automated feed of Healthmap data so that she can keep abreast of what's going on, and that can help her in her content. I mean, the other aspect is thinking about how we can collect better information from the field and from reporters. And the idea of really developing a true collaboration with a news agency like Reuters, CNN, thinking about how to then potentially get more structured information from those reports, because really we're trying to figure out all these elements in a news report, but if from the beginning a news reporter had all these elements, these structured content, then it would really solve a lot of the problems that we're actually trying to overcome. And so that to us would be an ideal situation as well. And the idea that we could do that for all news agencies is probably unlikely, but to partner up with one of the big ones would be an ideal situation. Yeah. All right, thanks. Anything? I don't know if there's anything over there. Okay.
Great. Well, thank you all for joining us today. And if you have any further questions about Healthmap or the work of the Predict and Prevent Initiative through google.org, please feel free to reach out. We look forward to bringing more tech talks and to continuing our work with Healthmap. So thank you very much.